In this video, we will be working with the same problem as before. It's a salsa production, and we have this formulation. Profit maximization, we want to know how many jars of each type of salsa to make, and we have so many ounces of whole tomatoes, tomato sauce, and tomato paste available, given to us, available here. In each constraint, we know how many ounces go into each jar of the various ingredients that we have. Let me bring up the POM data. This is exactly as I described it. If I solve, let me go to original problem with answers. So what we have here is the numbers that you see here in black, and I will increase the font a little bit so you can see this better. The numbers that you see in black is what I entered. W, under the W column, you see 560. Under the M column, you see 240. These are our optimal solutions. So we must make, linear programming tells me to make 560 jars of Western salsa, 240 jars of Mexico City salsa, and with that, I get $860 of profit. That is the best solution that I can get and the highest profit that I can make, given that I have so many ounces of whole tomato sauce and tomato paste. The way you will you can solve for see how that is done. If you come to the or how that $860 is made, if you come to the profit maximization objective function, and instead of W, if you plug in 560, and if instead of M, you plug in 240, you will get exactly 860 as the answer, which is the $860 of profit. I will expand okay. So these dual values that you see here are also reported if you go to the ranging window. So you go to the Windows menu and go to the ranging output. Now I will be spending most of the remaining time on interpreting this window right here. For one thing, remember or recognize that the 560 and the 240 values or optimal solution for Western salsa and Mexico City salsa are reported under the value column. For what? For variables. Also notice that in that section, the top section, which has to do with variables, you see a reduced cost and you see original value, and recognize that this 1 and 125 is really the 1 and the 125, that 1.25 that we had as the objective function coefficients for each of those variables. All right, and then we have a lower bound and we have an upper bound. So let's understand what these are. You already recognize that the 1 and the 125 are the original values. So this is what we had used as the coefficients of each variable in the objective function in order to get this solution that you see over here. The lower bound. Let's understand the lower bound. The lower bound for decision variable W says that this $1, which is the original value right here, this original value, $1 profit per jar, can be as low as 89 cents, well, 0.893, which rounded in order for us to be not go below it, we would really need to be 90 cents. So this $1 can be as low as 90 cents, or this $1 can be as high as $1.25. So the profit per jar of the Western salsa can range anywhere from 90 cents to $1.25. And you would still want to make 560 jars of W and 240 jars of M, or Mexico City. So the optimal solution does not change and remains the same, even if this $1 profit per jar of the Western salsa ranges in value anywhere from 90 cents to $1.25. This $1 over here as the lower bound and the $1.40 as the upper bound is essentially says exactly the same thing, but now for the Mexico City salsa, that even though when we solved the problem, we inputted $1.25 as the profit per jar of Mexico City salsa, that $1.25 per price per jar, or not price, but I'm sorry, profit per jar can be as low as $1 or as high as $1.40, and our decision would still be the same, to make 560 jars of Western salsa and 240 jars of Mexico City salsa. But these, okay, I'm gonna leave it at that. Now coming to dual values, these dual values right here, surplus or slack for each of the constraints, and then of course we have the original values and lower bounds and upper bounds for each of the constraints. So here now we're working with the constraint section. Notice, let's start here with the original value. Notice that these original values are the right-hand sides of each of the constraints that we inputted in order to solve the problem. So those are the original values. The slack or surpluses are to be interpreted in terms of the sign of the constraint that went into our formulation. So if the constraint has a less than sign, then we would interpret entries in this column as slack. So all of these constraints in our problem were less than or equal to signs. So all of these entries here in this column are really slack. If any of these constraint signs were greater than, then for that particular constraint, then the entry for it would be considered a surplus. Now, what is a slack or what is a surplus? When we go back to our, when we look at our formulation, for a less than constraint, we want the summation of the left side to be less than the right hand side. So a slack is how much this left side falls short of right side. On the other hand, a surplus would be how much the left side goes over the right side or exceeds the right side for a greater than constraint. Let's say, and this is not part of this problem, but let me just say that we have this relationship for W plus 8M less greater than or equal to let's say 1200. So in this situation right here, if I were to plug my W and M values, whatever they are, in here, and if this left side is higher than this 1200 by any amount, then that would be the excess, or how much I used up more than the minimum set, and so that we call a surplus. So coming back to our definition, slack is used in relation with less than constraints, and surplus is used in relation to greater than constraints, which in this problem we don't have any. So coming back here, the zero slack means that in this constraint for whole tomatoes, if I plug in the 5 and if I plug in the 560 and the 240 in this constraint, so I do 5 multiplied by 560 and 7 multiplied by 240, I will get exactly 4,480, meaning that my left side of that constraint, the left side is exactly equal to 4,480, and I don't end up with any idle amount or unused amount of whole tomatoes if I choose to make 560 jars and 240 jars respectively. The same interpretation can be done here for paste. So the zero slack means that for the paste constraint, 2 times 560 plus 2 times 240 is exactly equal to 1600. You can check this out on your calculator. On the other hand, here, the 160 slack ounces of sauce tell us that if I take 3 and multiply it by 560 and 1 multiplied by 240, the amount that I end up with is going to be 160 units or ounces less than 2080 ounces that I have available of the sauce. So that's what the interpretation is here. Now let's relate that to the dual values. If I run out of a resource like the whole tomato and the tomato paste, then it makes sense that assuming I have more of it, assuming I would have more of it, my objective function and my solution could be better. So with making 560 jars and 240 jars, I would use up all of the whole tomato and all of the paste. So let's look at the whole tomato. For every ounce of whole tomato that I have, that I can get my hands on, my objective function value will improve 12.5 cents. So because the objective function value was $860, for every extra ounce that I have over and above the 4,480, then my objective function would improve 12.5 cents. The same thing here. For every ounce that I have available extra over and above 1600 ounces of paste, my objective function would improve in value 18.8 cents. Notice that the dual value is always in the same units as the objective function. So because our objective function is profit, so this 860 objective function value is dollars, $860, and the dual value, or the change to the objective function, would also have to be in dollars. I'm going to stop this video because I think it's very long now, and I will continue with the continuation of it, or with the rest of this interpretation in the next video.